We are live and we continue solving our task. So we have to return the median of the two sorted arrays. The overall runtime complexity should be n log O log n plus n. So what does it mean? We cannot use here linear approach like 1, 3, so we cannot merge and then find. It should be less. So we need to find median maybe here. But actually it can be all. It can be different approaches here. So for that 1, 2, 3, 4, 2.5, it should be double. Okay. Okay. They are two sorted. So let's check and try first to understand the problem. So if we will understand the problem, actually we can have something like this. Like first array would be like this, and second array would be like this. And the question, can we have duplicates here? Because I cannot say in description, so probably let's sort first without duplicates. So here we see that this 3, 4 is actually going here, and we should take all values here. So what options we can do? First, maybe we can find some middle element, or like middle here, and then here. So when we find the middle element, we see that we have 1 and 7. And here we have 3 and 4. So it means that it's going here. And it means that we can actually add this size plus mid, and then we can calculate the next mid. If, for example, we have like 12, 13, then size should be decreased by, mid should be decreased by size of 2. And here mid should be increased by size of 2. Yeah, so we have these two options here. Another option that we can have cross boundaries. So for example, we have like 1, 2, then 3 and 4, right? So here we have 1 and then we have 3. Yeah, and it's more complex here. Because 3 is greater than 2. Yeah, I need some hint here. Divide and conquer, okay. Yeah, merge sort, its complexity is not correct. We can use merge sort, but yeah, time complexity would be n plus n. And binary search recursive, we can use something like this. Yeah, because we see that it's hard problem, so yeah, definitely it's not an easy way to solve it. better binary search. Yeah, and with this one it works. Do you see that it's quite complex? Yeah, I think that something like this they're doing. Actually, right? Partition 8, partition B. Okay. Okay. Max left, max right, max left, max right. Complexity. And be the size of array. Outside and the size of complexity. Yeah, maybe we saw. Yeah, so we saw it long time ago. Yeah, but it's here merge sort. So yeah, so I saw it, but with merge sort. But I think merge sort not the best. Not the best. So let's find our solution and let's try to understand, because I think with this understanding, I think it's something similar that we can use here. So let's find. So intuition, because the inputs are sorted arrays and the problem asks for a logarithmic time limit, we strongly feel that binary search is promising method. Yeah, that's true. While we are not sure how the cast the same pattern as normal binary search on this problem. So let's go over some steps of regular binary search and see if we can get any inspiration. If you are not familiar, so we're familiar. So here we use binary search to find the target in a sorted array A. Okay, so it's just the target. So we locate the middle, we compare with target, we reduce the search, and we repeat this until we will find. So for example, we are looking for 26. So first 9, we eliminate this one, then this one, and so on. At each step, the search space is cut to half, yes. So we can quickly get the result. Now, back to this problem where we have two sorted arrays. For the sake of the convenience, let's call them A and B, right? So we have A and B, and we have some middle elements in A and B, right? Similarly, we can get compare their middle values without loss of generality. In this example, we assume A mid is less or equals to B mid initially. So for example, we have 3 and 7. So what does this comparison imply? If it implies that we can compare sections A and B. Mm, ah, okay. What does this comparison imply? It implies that we can compare sections of A and B. Yes. For the rest of this article, we will use less or equal to represent the relative magnitude of values in array. For example, A left is less or equals or than right. Means that every element in the A left is no longer larger than the element in the A right. Yeah, so that's true. Yeah, so that's true. We also compare elements in the array with a single element. For example, a left. Okay. This may not be the most standard way of expressing it, but it's easy enough to understand. Recall that both arrays are sorted, so we know that a left is less than a mid. So definitely this value would be less than all this value, but we can actually have this value here. Somewhere we can have 3, for example, right? And we don't know about this value, whether it would be smaller or not. We just know that this value is smaller than 7. So we can actually put it here, right? Then we have 3 and 7. So we decrease the first part. Then we try to find here mid and compare. Okay. Okay. Combine this observation with the comparison we just made. So a mid. Okay, we have the following result. So a left is left the a mid, right? And this one is less than a mid. Yeah, so we actually, what do we have? B mid and B right. So we have this sorted array, right? Something like this. But we don't know about this one, right? So we have like this. Since A is sorted, we know that A left is greater than yes. Now we know that A left is smaller than 2 halves A right and B right, yes. So that's for sure. So this one is smaller. But we don't know about this one, right? Also, we still do not know whether exactly this one are. What we do know is A left doesn't intersect A left doesn't with A right and B right. Yes. So, but with this one, it can intersect. There is an invisible boundary between A left segment and the mixed segment A right, B right, as shown in the picture below. The dashes line divides all sorted elements into 2 halves, right? So we can see that we have A right and B right, and here all A left. So definitely we can have this. We can apply all the same logic to the mixed segment A left plus B left and B right, which also do not intersect. You can try to prove it yourself. Okay. It looks somewhat clear. We have clearly separated some subarrays. How do we continue leverage this knowledge and use the cut in half method repeatedly? The following steps is the most important one. Remember that we are looking for the median of sorted A plus B, which is 1 or 2 target values. We regard the index of the target value in the sorted A plus B as k, for example. If the lengths of A and B are 6 and 5, the target index is 6 plus 5 plus 1 divided by 2. We should look for the 6 smallest elements. If the lengths of A and B are 6 and 6, the target index is 6 plus 6 divided by 2. And k plus 1 equals 0. We should look for the 6 and 7 smallest element. Depending on whether the total number of elements is odd or even, we need 2 k's, and maybe we need k plus 1 elements. What matters is that we set an index k at the beginning, and we want to find the key smallest element using the binary search like algorithm discussed previously. However, during the binary search like algorithm, we keep moving 1/2 of an array, so the index k might not stay unchanged. Suppose we remove 3 elements. Okay. Remember original A and B. So k 6 plus 5 divided by 2 is 5. We are looking for the fifth smallest element. We remove the smallest half of that contains 3 elements, and k it would be 3 plus 5 plus 5 minus 3, 2, and we are looking for the second from the remaining arrays. Why is 5 minus 3? If k is larger than half. Okay, let's check. So we have a in the left. Let's check how it works. So we have A and B, left and right. Remember that we are looking for the k smallest number, because considering 2 cases. Plus b divided by 2. Okay, so let's define, so let's check how it looks in the code. So first we check lengths, then we have the total lengths, and then we see if equal to 1, it means we need only one element, otherwise we need 2 elements. So here we have A and B, then we have K, A start, A end, B start, B end. Okay. Here we do some recursion call. Okay. Better by recall the previous program over merge 3. Largest half, smaller half. The next step is to compare these edge elements. Okay. Let's check how it works. It's also recursion. So we have partition 1 and 2, min max left, min right. Okay, if max left, mass return max. Yeah, let me try. So yeah, I think we already like 20 minutes more, so let's stop for today.